in the previous lecture, we have discussed the energy conservation in central force field, and you have also seen the equation of orbit or equation of trajectory in general form for a particle moving in a central force field. Now, as I have told you in that lecture, that we will illustrate the concept of energy conservation and the uh, equation of trajectory by taking some important examples. So in this lecture, we will illustrate the concept of the energy conservation and also the equation of trajectory by taking some important numerical problems. And this type of problem is frequently asked in your examinations, both in university examinations and competitive examinations. So definitely this session will be very useful for you. So be serious and watch the video seriously. Definitely you will enjoy that the concept which we will actually adopt to solve the problem is very easy, and going through these some important examples you will be able to solve so many problems from your textbook. Okay, so let us see. I have selected here actually three problems, but after solving these three problems, a concept will be developed, and you can follow the concept developed in this in the solution of these problems to solve some unknown problems from your textbook. Okay, so let us see what is our first problem. The first problem says a particle of mass m moves in a central force field defined by F equal to minus kr over r4, where k is a constant. Okay, force is defined. Then we have to show that if E is the total energy supplied to the particle, then its speed will be given by this expression. Okay, that is V equal to a square root of k over mr square plus 2e over m 2e over m. We have to prove this result. Okay, so what is given in this problem? In fact, the central force under which the motion is taking place is defined, and the total energy of the particle is also given, which is E. Then we have to find what will be the speed of the particle. This is a very simple problem. In fact, in the previous lecture, we have derived the expression for the total energy of a particle moving in a central force field. So writing the expression for the total energy of the particle moving in a central force field, you will be able to solve this problem. Okay, so let us see how we can solve this problem. Can you remember what was the expression for the total energy of a particle moving in a central force field? Definitely you should remember it. If you cannot remember, go through the previous lecture. You will see the expression for the total energy in that lecture. So must watch that video. So the total energy of a particle, total energy of a particle moving in a central force field, moving in a central force field, you know, it is given by E equal to what? This is, you know, half m r dot square plus j square over 2mr square and plus V of R. Okay, this expression I have derived in the previous lecture, so I have written it here directly. In fact, you know this the sum of these first two terms actually represents the kinetic energy, and this last term is the potential energy. Okay, and as you know, this J is what? This is angular momentum of the particle. Okay, angular momentum. Now, as you know that the expression for angular momentum of a particle is what? This is mr square theta dot. Okay. So let us put this expression for J in this expression. So you will get this is half mr dot square plus mr square theta dot whole square and over 2mr square. Okay, and plus V of R. Okay, now this will be half mr dot square plus. Now when we will simplify this second term, you can see one of the m in the numerator will cancel out, and your result will be what? This will be mr square theta dot square, mr square theta dot square. Okay, and also there will be 2 here divided by 2. Okay, okay, and plus V of R. Okay, now you can take this half m as a common factor in the first two terms. So this will be half m r dot square plus r square theta dot square and plus V of R. Okay, now you can see that r dot square, this is nothing, this is simply the radial component of velocity, you know. So this is Vr square, and the transverse component of velocity you have studied earlier, this is simply r theta dot. So r square theta dot square, this will be V theta square. This is transverse component of velocity. Okay, and V of R. Now Vr square plus V theta square, this will be V square. So this will be simply half m V square plus V of R. Okay, this is the expression for E. Now you can see, although I have arrived this result by simplifying the expression for the total energy, but you can see the previous video, all these things I have done already. So if you want to solve this problem in a very little step, you can write this expression for the total energy directly. So E can be written equal to half mv square plus V of R directly. Now as in our problem, we have to find the value of V. So you can see what will be the value of V from this equation. From this you can find half mv square, and this will be equal to E minus V of R. Okay, and therefore V will be what? This will be in fact 2 times E minus V and over M. Say this is equation 1. Now from this equation you can easily see, if we calculate the value of the potential energy V and substitute that value in this equation, then definitely we will get the expression for the velocity or speed of the particle. So now let us try to find the actual value of potential energy V. I have only written this expression, its symbol, but what will be the actual value of potential energy in the present situation? Now we can calculate. As in our problem, the central force, which is actually a conservative force, it is defined here. You can see in your problem, it is given that F is equal to minus K vector R over R4. Okay? You can see that this force is in fact an attractive central force. This is an attractive central force. Attract, because here there is minus sign, so this force is directed towards the center of the force, and so it is an attractive force. So you can write as in case of central force, you write that F is equal to what? F is equal to, symbolically we write F of R times R hat. Okay? And this will be equal to what? Minus K and R. R, vector R can be written as R times R hat and divided by R4. Okay? So now you can see that what will be this F of R, which represents actually the magnitude of the force. So F of R is simply equal to minus K over R cube. Okay? Minus K over R cube. This minus sign actually represents that the central force here is attractive. Okay? Now I have actually discussed earlier when we have seen the conservative nature of this central force, that the potential energy corresponding to this central force is defined like this. So V of R, you know, this is defined by minus integral F of R dr from reference infinity to R. Here actually R equal to infinity is the reference taken for calculation of potential energy. It means you are assuming that potential energy is 0 when R is equal to infinity. Okay? So this is just reference. Now let us substitute the value of F of R, which is defined here. Since F of R is minus K over R cube, and in this formula already minus sign is present, so when you will substitute this value, what will be the result? The result will be integral infinity to R and K over R cube dr. Okay? And now you can see K is constant, and 1 over R cube, integral of 1 over R cube, this will be in fact minus 1 over 2 R square. And limits are what? These are R and infinity. Now let us put the limit. This is minus K over 2, and after substituting the limit, this will be 1 over R square minus 1 over infinity square. And this is simply minus K over 2R square, because 1 over infinity is 0, you know. So we have calculated the value of potential energy, and this potential energy V of R is simply equal to minus K over 2R square. Okay? Now substitute this value of V of R, which you have obtained here, in this equation which we have obtained for the speed v of the particle. Okay, so this is v equal to 2 times e minus v over m. Let us substitute this value in this equation. So what will be our result? You can see, therefore v is equal to 2 times e minus v over m. Okay, and this will be 2 over m and e minus and there will be also a square root here. See, here v will be a square root of this much, because v square will be this, so this is a square root of this much. Okay, a square root of this much. Now let us put the value of v. This is e minus v. V is minus k over 2 square, so this will be plus k over 2r square. Okay, and a square root. Okay, so you can see this expression in RHS can be written as, this is 2e over m and plus k over mr square. K over mr square, and for a square root I am writing here power 1 by 2. So you can see this is the expression for a speed which was to prove in this result. Okay, I think the solution is very easy, very simple, and you have definitely understand the solution very easily. Okay, now we will see what is our second problem. See here, this is your second problem. The second problem says that a particle is moving in a central force field located at r equal to 0. It means r equal to 0 is the center of force. Describes the spiral r equal to e to the power minus theta. This is actually equation of trajectory. Okay, and then we have to prove that the magnitude of the force is inversely proportional to r cube. Okay, it means in this problem we are given the trajectory followed by the particle during its motion in this central force field, and we have to find the central force, or in other words, you have to show that this central force depends on r as inverse of the cube of the distance. Okay, this is also a very simple problem, and you can easily solve this problem. Since trajectory is given here, so this problem will be easily solved by starting with the equation of trajectory, which you have actually studied in the previous lecture. So starting with the equation of trajectory, you can obtain that the central force under which this particle is describing this spiral path will be definitely inversely proportional to the r to the power 3. How we can solve it? You see here. Now you know in equation of trajectory the parameter r is changed in terms of a new parameter u, and both are related by this relation. We know that r is equal to 1 over u. Okay, 1 over u. And as in this problem, the equation of trajectory is given r equal to e to the power minus theta. It is given. This is equation of trajectory. And so you can say that this u will be what? This u will be 1 over e to the power minus theta, that is e to the power theta. So this is actually the equation of this is actually the value of parameter u. Okay. Now, as in case of equation of trajectory, uh, we need the second order derivative of this u with respect to theta. So first of all, we will obtain the second order derivative of u with respect to theta. So you can see from here that what will be du d theta. See here. Since u is equal to e to the power theta, so du d theta will be also equal to e to the power theta, and this implies d2u d theta square. This will be again e to the power theta. Okay. So now we know the value of u and the value of d2u by d theta square. So now, first of all, write the expression for the equation of trajectory, which will be actually the general equation, and from that equation you can easily show that the central force under which the particle is moving will be definitely inversely proportional to r cube. You can be able to show this. So let us start with the equation of trajectory. Now the equation of orbit or trajectory, you may say, is given by, you have studied this equation in the previous lecture and you can remember, this is d2u d theta square plus u equal to what? This is equal to minus m times f of u, or you can say f of r, and divided by j square u square. Can you remember this result? Definitely you should remember, because we have studied this thing in the previous lecture. This is actually the general equation of orbit of a particle moving in a central force field. Okay. And as in this problem we have to find force, that is we have to calculate f. So let us write this equation in this manner. F of u will be what? This will be minus j square u square over m times d2u d theta square and plus u. Okay. This is a very simple algebra, you can see. Now you can see we have obtained that u is simply equal to e to the power theta. Sorry, the page has been turned, but it will be just okay, don't worry. This is just a minor defect of my device, so, and it always takes place. Sorry. So now let us see that u is equal to e to the power theta, and d2u d theta square is also equal to e to the power theta. Okay. So let us substitute these two values in this equation here. You can see this will be minus j square u square over m and times, as d2u d theta square you have seen this is e theta, e to the power theta, and u is also e to the power theta. Okay. And so this is what? This is minus j square u square over m times 2e to the power theta. Okay, 2e to the power theta. Now again here there is u, so again write instead of u, you can write e to the power theta. Okay, so this will be minus j square over m times u square. U square means what? This is e to the power theta whole square, because u is equal to e to the power theta, you have seen, and times 2e to the power theta. Okay, so what will be this? This is minus j square over m times 2 e to the power theta times e to the power 2 theta, e to the power 2 theta. And this result can be written as minus j square over m and times 2 and e to the power theta times e to the power 2 theta. You can write it e to the power theta to the power 3. Okay, to the power 3. But you know that e to the power theta, this is equal to u. So what will be this? This is minus j square minus 2j square over m times u cube. This is u cube. Okay, u cube. But you know that u is equal to 1 by r. So now when we will change the parameter u to r, what will be our result? So u is now changed in terms of r. So f of r, this will be equal to minus 2j square over m times 1 by r cube. Instead of u cube, I have written this. Now you know that in a central force field, during the motion in a central force field, this j remains constant. Angular momentum of the particle remains constant when the particle moves under a central force field. So from this you can say that this 2j square over m is a constant factor, and therefore this f of r is inversely proportional to r cube. Okay, and this is the result which was to prove in this problem. Again you can see, since f of r has been obtained negative, so this minus sign implies that the central force defined in this problem is an attractive central force. It is an attractive central force. Attractive. Okay. So you can see this problem has been also solved very easily, and there is no rigorous calculation, no rigorous concept. Only if you have the equation of trajectory in your mind, you can easily solve such type of problems. Okay. Now we will see the third, that is the last problem of this session. You can see the third problem says that a particle describes a conic r equal to p over 1 plus epsilon cos theta, where p and epsilon are constants. Okay, this is actually the equation of trajectory of the particle moving in a central force field. In fact, in this problem we have to show that the force under which particle is moving is an attractive central force obeying the inverse square law. What does it mean? If the particle describes a path whose equation is this, then we have to show that the particle is moving in a central force field. and that central force field will be definitely attractive, and that will actually vary inversely with the square of the distance. This is to prove in this problem. Okay. Again, you can see that here R is given, it means U is given, and we have to find the force. So this problem will be also solved in the same manner as you have solved the second problem. It means starting with the equation of trajectory, you can easily find the force which is responsible for motion of that very particle. Okay, so let us see the solution of this third problem. In fact, you can see in this problem we are given, what is given? R equal to P over 1 plus epsilon cos theta. It is given in this problem, where P and epsilon both are actually constant factors. Okay. Now you know that this R is equal to 1 over U. So this is simply 1 over U, and this is equal to P over 1 plus epsilon cos theta. Okay. And so you can say U will be what? This U is equal to 1 plus epsilon cos theta over P. Okay. Now, as you have seen in the previous problem, when we will apply the equation of trajectory, we need two quantities. First one is U, which is already defined here, and another is d2u d theta square. We need these two quantities. So let us now try to find the second order derivative of u with respect to theta. So from this equation you can see, first of all we will find du d theta. And what will be this? Since p is constant, so we will differentiate it, and 1, when 1 will be differentiated, this is 0, and cos theta's dc will be minus sin theta. So this is minus epsilon sin theta and divided by p. So this is simply minus epsilon over p sin theta. This is du d theta. Okay, du d theta. And from here you can find what will be d2u d theta square. That will be simply minus epsilon by p cos theta. So this is a very simple differentiation, and therefore you can write d2u d theta square. What will be this? This is minus epsilon over p cos theta. So you have obtained the value of d2u d theta square, and you have also find the value of u, which is defined here. So now write again the equation of trajectory to find the force responsible for this motion. So now equation of trajectory. Equation of trajectory or orbit you can say is given by, since we have to find the force, so I am just writing directly the expression for force in terms of equation of trajectory. So you know f of u, this is equal to what? Just we have seen, this is minus j square u square over m times d2u d theta square plus u. Okay. Now let us substitute the value of d2u d theta square and u in this equation, which you have obtained earlier. So this is minus j square u square over m. And you can see d2u d theta square. This is equal to this much, minus epsilon cos theta over p. Okay, and plus u. What is u? You can see here, u is equal to 1 plus epsilon cos theta over p. So put this value of u here. So this is 1 plus epsilon cos theta over p. Okay. Now let us simplify the RHS of this equation a little bit. So this will be minus j square u square over m. Okay. And this will be minus epsilon cos theta plus 1 plus epsilon cos theta over p. Okay. This is just a simple calculation, and so this will cancel out, and what is your result? You can see this is minus j square over mp times u square. Now u is equal to 1 over r, so I am just writing it here. You can see this. Now u will be changed to r, so we write f of r, and this will be equal to minus j square over mp times 1 over r square. 1 over r square, because u equal to 1 by r. So you can see again that the force obtained here is negative, and this minus sign, as I have told you earlier, both in this lecture and also in the concept of a central force earlier, that if f of r is negative, that minus sign only implies that the central force is of attractive nature. So this minus sign does not affect the value of the force, it represents the nature of the force. It is just an indication that this central force is an attractive central force. So we have to show in this problem that the central force is attractive. So you can see that this central force is attractive due to this minus sign. It is proved, and at the same time you can see that the magnitude of this force is inversely proportional to r square. So you can say that this f of r is what? This is an attractive central force, and it obeys the inverse square law, because f of r is proportional to r to the power minus 2. So we simply say that this force obeys the inverse square law, like gravitational force, like electrostatic force. This force is just an inverse square law force. So this solution was also exactly like the solution of problem number 2, and I hope you have been completely acquainted or to solve such type of problems. So whenever a problem will be asked of this type, you should remember the equation of trajectory to find the force, and after getting the value of force, everything will be clear, that force is either attractive or it is repulsive, and how it varies with distance r. Okay, so after this lecture we will now in the next lecture see the solution of the equation of trajectory which we have used in this lecture, and after the solution of that equation you will get so many useful results which will be actually very very interesting, and you will enjoy, I hope.